Hello everybody, my name is Elena Michalcia. Please let me present you the poster I prepared for the 34th International Material Research Congress 2026. So the name of my poster is The Effects of Hydroxyapatite Addition on the Corrosion Behavior of the Titanium 25% tantalum and hydroxyapatite alloy, fabricated by Spark Plasma Sintering. Alright, let's begin with the abstract. So the titanium 25 tantalum alloy has been shown to present the best combination of properties for biomedical application. This in comparison to the widely used titanium 6 aluminium 4 vanadium alloy. However, the main disadvantage is it is low to medium ability to promote bone regeneration. So thus, to overcome this disadvantage, the addition of hydroxyapatite was studied in this work. In order to reach our objective, the titanium 25 tantalum and hydroxyapatite alloys were obtained by mechanical milling. Different quantities of hydroxyapatite were added from 1% to 5% atomic percent. The powders were milled for 25 hours under dry conditions. Then the milled powders were poured into a graphite dye and sintered by spark plasma sintering, also known by SPSS, at a temperature of 1200 degrees Celsius and under a pressure of 50 megapascals at high vacuum. So the microstructure was observed by Scanning Electron Microscopy, or SEM, and also we used the X-ray diffraction. The results show that the addition of hydroxyapatite reduces the densification of the samples during the sintering, and that's because there is no diffusion between the hydroxyapatite and the titanium 25 tantalum alloy. Well, despite that, the relative density reached were larger than 90%. The microstructure is mainly composed of beta titanium phases, and the hydroxyapatite particles are randomly displayed and dispersed. Corrosion was evaluated by potentiodynamic test, and this under Hank solution. We use that as a simulated body fluid. The corrosion behavior indicates that the hydroxyapatite addition improved the behavior of the composite, and that by reducing the corrosion rate and also turning the corrosion potential, the Ecorr, to a more positive value. And besides, the passivation film, its form, a passivation film is formed, and like this is more stable as the quantity of hydroxyapatite increased. So it was concluded that the addition of the hydroxyapatite favors the behavior of the titanium 25 tantalum alloy in the corporal fluids, in the body fluids. And this could be used for biomedical applications. This is our interest. That's why we tested it in the body fluids. And the best combination seems to be the 5% atomic percent of hydroxyapatite added to this alloy. All right, very good. But you have an idea of what this poster is all about. Following, let's have a look at the experimental method. We are going to begin with the fabrication of the powders. And as we explained, it was by mechanical milling. Let's have a closer look. So the fabrication of the powders. Basically, we are going to use titanium powder mixed with tantalum and hydroxyapatite, as we mentioned. So the initial powders are weighted to obtain a stoichiometric ratio of the titanium-25 tantalum for 50 grams of the alloy. Then the hydroxyapatite is added, and in weight percent of 2 and 4% to the titanium-25 tantalum alloy. All these powders are poured into the container of a high-energy ball mill specs 8000 M. Here we have an image of this mill. So we add the powders into the container together with two 12mm diameter stainless steel balls. So the milling time of the titanium-25 tantalum was 24 hours, and an additional 2 hours were used to mix also the hydroxyapatite with the titanium-25 tantalum alloy. All right, that's all for the fabrication of the powders. Now let's continue with the sintering at step. So as we mentioned, we use a Spark Plasma Sintering, SPS. Here we have a picture of the machine, of the SPS machine. Some of the characteristics of this SPS machine are the rapid heating rates, the fact that it's pressure assisted, we have axial shrinkage. We should mention this is an expensive equipment. Now let's have a look at some of the parameters we used for our sintering. So it was under a temperature of 1050 degrees Celsius with a 50 degrees Celsius minimum under a high vacuum atmosphere and a pressure of 50 megapascals. All right. And the last step of our experimental method, it's the potentiodynamic test. All right, so the potentiodynamic tests were done under a simulated body fluid, as we mentioned, the HANK solution. And here we have our tank with our sample in an electrolyte solution. This is connected to the potentiostat. When we have electrochemical analyzer, let's have a better look. Let me zoom. All right, all this is connected to a PC. And we have a control and data acquisition module, and we can obtain our control and data acquisition curve, our corrosion curve. So we have a graph between the current density versus the potential, and all this is the output display and analysis, and it is used for the analysis of the corrosion tests. All right. Let's continue with the results. Just a moment. All right. So the first part of the results, we are going to have a look at the kinetic curves from the SPS data, from the Spark Plasma Sintering machine. So in here we have two curves. One is the relative density versus temperature in degrees Celsius, and the other one is the strain rate versus temperature. For the two graphs, we have three curves corresponding to the titanium-25 tantalum alloy. This one in blue. In red, we have the curve for the titanium-25 tantalum with 2% of hydroxyapatite, and the green one is for the titanium-25 tantalum with 4% of hydroxyapatite. And as we can see from the curves, is that what we can see is that the sintering by the spark plasma sinterings allows to obtain dense samples with a pore volume lower than 3%, and also that the densification is reduced by the addition of the hydroxyapatite particles. All right. Okay, let's continue. With the results that we obtain from the X-ray diffractometer. And in here we can have a look at the X-ray patterns. Basically what we can see, especially in here, we can observe that the microstructure is composed of 4 phases. Here we can see these 4 phases. So we have the alpha, we have the beta, and we also have the spikes corresponding to the alpha prime and also the alpha double prime. See? Alpha prime, alpha double prime. See? Another thing we can observe is that we have no spike for the hydroxyapatite, basically because it was too low. So we can say that hydroxyapatite is not detected by our X-ray diffractometer. See, at least not in this pattern. All right. So we have the same thing. We have three patterns. One is for Ti25 tantalum for hydroxyapatite. Another one is for the Ti25 tantalum with 2% of hydroxyapatite, and the other one is for titanium and tantalum. All right. Let's continue with the results. And in here, I'm going to present you the same images. The images were obtained from the scanning electron microscopy. All right, so in here we have the images from for the Ti25 tantalum. Here are the SEM images from the Ti25 tantalum 2% of hydroxyapatite, and in here it's for the alloy with 4% of hydroxyapatite. So in here we have the images from the electron microscopy, and here is basically a zoom. It's the same image but with a zoom in. If we do a zoom, we can observe that we have a titanium tantalum in a lamellar form. In here we can have a look, and we observe that we have small pores, and in here we can observe that the titanium tantalum after the sintering gets a more rounded face, we can call it. See? So the conclusion was that small isolated pores remain, which confirms the high densification reached by the alloy after the sintering. And we also can conclude that the addition of the hydroxyapatite breaks the lamella formed by the titanium tantalum into a more rounded face, and it's homogeneously distributed on the surface, as we can see. Okay. Also, if we have a look at the EDS mapping, also in the images obtained by the scanning electron microscopy. So these images are SEM images with an EDS mapping. Let's have a better look at that. Let me zoom in. Okay. So basically, maybe a little more. Just a minute. So in here we have the initial image. In here we have the image where we separate, where we can see all the components: tantalum, titanium, calcium, phosphorus. In here we have a mapping for the tantalum. In here for the titanium. In here is the calcium, and in here is for the phosphorus. And what we can see is that the tantalum is concentrated in the brightest phase. If you're talking about the tantalum in here, so in red is the tantalum. So the tantalum is concentrated in this, as we can observe, the brightest phase, which confirms the stabilization of the beta titanium and suggests the formation of martensitic phases like alpha prime and alpha double prime. So alpha prime and alpha double prime are martensitic phases of the titanium that are formed when the beta phase of the titanium it's rapidly gets cold. All right, and in here we can, for example, for the hydroxyapatite, so we have the components of the hydroxyapatite, so the calcium and the phosphorus. And what we can observe from these two images, microscopic images, is that the hydroxyapatite seems to be homogeneously distributed. Same, yes. And the titanium, it's more like it's in green in here. All right. All right. And last, I'm going to talk about the potentiodynamic curves we obtained from the potentiometer. And as we mentioned, these curves were obtained under Hanks solution. In here we have again the three curves for the titanium 25 tantalum, and the other two for 2% and 4% of hydroxyapatite. And what we can see is that the addition of the hydroxyapatite reduces the corrosion resistance. The 4% is the lowest one, is reducing the corrosion resistance, and the corrosion behavior, in conclusion, could indicate that the hydroxyapatite is reacting with the Hanks solution, and probably to form something like the bone precursors. All right, let me finish with the conclusions. So the Spark Plasma Sintering allows the production of titanium 25 tantalum with hydroxyapatite composites with low residual porosity. The microstructure confirms that the tantalum addition stabilizes the beta titanium phase. Besides, the fast cooling induces the formation of these martensitic phases like alpha prime and alpha double prime. The hydroxyapatite seems to be homogeneously distributed in the alloy, and induces the segregation of the lamellae phase, la beta, and its transformation is more like a more rounded phase. The sintering kinetic is slowed by the hydroxyapatite addition, but however, due to the small particle size of the hydroxyapatite, the green density increases, which permits obtaining near fully dense compacts. And the last conclusion was that the corrosion behavior is hardly affected by the hydroxyapatite addition by showing lower values of Ecorr corrosion and Ecorr. And this is probably because the Hanks solution is reacting to form probably new minerals that could be beneficial for the bone ingrowth. All right, that's all for for my presentation. Thank you so much for your time. Have a very nice day. Bye.